Hey everyone, in this AP Chem series video, we're going to take a look at the periodic trend in atomic radius within a column on the periodic table. Remember, in the last video, we talked about the trend in atomic radius as you moved across a row, like we've got here highlighted for period 2. In general, the atomic radius will decrease from left to right, meaning the big atoms are here on the left and they get smaller and smaller as you move to the right. This trend exists because within a row, all of the atoms have outermost electrons in the same energy level, but the effective nuclear charge as you moved left to right will increase. This means there's a greater attraction between the outermost electrons in the nucleus that pulls those electrons in closer, causing you to get smaller atoms on the right-hand side. We can see that modeled here with some of these selected atom sizes. In this video, we're going to take a look at how this trend works as you move up and down within a column. So let's get started and analyze this trend down a group. To do that, we're going to focus on just one group. That's group 17, the halogens, highlighted here in green. We're going to talk about this trend moving from the top of the column to the bottom, and everything we say for group 17 can apply to any other group on the periodic table as well. To make the analysis, I'm going to use the same modeling system we did in the last video. For some of the atoms in the column, I'm going to show the nuclear charge represented here, followed by the electron configuration so we can get a sense of what's going on. So let's do that for just fluorine, chlorine, and bromine. That should be enough to see how the trend works. So the first thing people usually notice when looking at the atoms within a column is the nuclear charge. +9, +17, +35. Not only does it increase as you go down, it increases by a whole lot. And if you follow the same thinking that we did when analyzing the trend across a row, that increase in positive nucleus might make you think that these outermost electrons get more strongly attracted to that more positive nucleus and it pulls them in closer, leading to smaller atoms. And that thinking is correct, but there's another factor that's changing along with that increase in nuclear charge, and that is the shielding, or the effect of these inner core electrons, which also increase as you move down. To show you what I mean, let's actually calculate not just the nuclear charge, but the effective nuclear charge to see how this shielding weighs in. For our fluorine atom, its nuclear charge is +9, but if you factor in these two core electrons that are doing some shielding for these outer ones, the effective nuclear charge is decreased to +7. If you do the same thing for chlorine, you'll see that yes, the nuclear charge is way greater at a +17, but now there's also a lot more core electrons doing a lot more shielding. There's 10 of those if you count them, so take that +17, subtract out your 10 shielding electrons, and you get the exact same effective nuclear charge in chlorine as you did for fluorine. And that effect continues down to bromine. If you do the calculation there too, the effective nuclear charge is exactly the same. So while it looks like the nuclear charge is increasing, that effect is actually canceled out by the increased shielding electrons. So the effective nuclear charge that these outermost electrons will experience remains constant as you move down a group. So if the nuclear charge isn't playing a role here, what can we look at to explain the difference in radius? Well, luckily it's a much simpler explanation. All you have to do is look at where the outermost electrons are. I've got them highlighted in red. For fluorine, the valence electrons are in the second energy level, third in chlorine, fourth in bromine. So the outermost electrons, as you move down a column, they're simply filling higher energy levels. What's the difference between those? Well, as you go to higher energy levels, you are farther from the nucleus. That's the difference between a fourth energy level and a third and a second. They just get bigger. And if the atoms are in higher energy levels that are farther from the nucleus, that of course is going to lead to larger radii as you move down. We can see that here with fluorine's 50 picometers up to chlorine's 100 and bromine's 115. Let's summarize that by saying that in general, the atomic radius will increase from top to bottom in a column. This is despite an increase in nuclear charge because that increased shielding results in an effective nuclear charge that remains constant. So the explanation is because of the outermost electrons filling higher energy levels farther from the nucleus, resulting in atoms with larger radii. Make sure you jot down these key ideas. So let's close the video by talking about how to remember the overall trend, not only across a row, but also within a column as we move forward. I like to do this just by seeing a visual of where the biggest and smallest atoms are located. Here's one that shows the biggest atoms on the bottom left in spheres and the smallest ones in the top right. Here's another using a bar graph method. If you're taking notes, I like to draw a quick blank periodic table. You can do this with arrows, an arrow pointing down labeled as an increasing radius moving down, an arrow pointing left labeled with increasing radius pointing left, or simply label the corners. The bottom left has the biggest atoms and the top right has the smallest. I would recommend pausing and writing this version down so you've got it for later. You may have also heard of some exceptions to this general trend, things that go against our general rule of getting bigger as you move to the left. One of those has to do with the transition metals, and those exceptions do exist, but as of 2020, the AP Chem exam shouldn't ask you about those, so we're not going to cover them in this video. And that wraps it up for this video on atomic radius trends. Thanks for watching, and here's a brief summary.